This presentation's on kinetics, or reaction rates, chapter 14 in the textbook. There are a lot of factors that affect the rates of a reaction, but the main thing to understand is that it is all about collisions. In order for you to have a reaction, substances must collide with the right orientation and energy in order to have a successful reaction. Things that help are the state of the reactants, the concentrations of the reactants, the temperature of the reactants, and the presence of a catalyst. The state of the reactants, if you have a gas, it's going to be able to react easier than a solid or liquid would. If you have a solid that's powdered, where you have a lot of surface area, that's going to react quicker than a big chunk of a solid. Concentrations, just because if you increase the concentration, you're going to have more collisions taking place because some more particles are going to be in there. The temperature, because if you increase the temperature, you're also going to have more collisions because the particles will be moving faster. Also, though, the temperature comes with an increase in the amount of activation energy, which we'll talk about later. And the presence of a catalyst is a benefit because the catalyst will give you either an alternative pathway for the reaction to occur, or will provide you with something that will hold the orientation in the direction that you want it, like an enzyme, so that the reaction is more likely to occur. So the higher the number of the collisions, the higher the reaction rate, the higher the energy of the collision, the more likely you are to get a product. So here's a picture that demonstrates the orientation factor. Only a tiny fraction of collisions will result in a reaction. It's different for each type of reaction going on, but the number of collisions that results in a reaction could be in the order of 10 to the negative 13th, or 10 to the negative 15th, or 10 to the negative 10th. So catalysts are one of the things that can help with this orientation, but in this case you have particles coming in, and it's some sort of chloride with a chlorine atom coming in, and they collide, and in the top one, after they collide, the reaction had occurred, so you have two new particles. But if the orientation is different, and instead of the one chlorine atom hitting another chlorine atom, it hits an oxygen or a hydrogen or something like that, then there's not going to be any sort of reaction after the collision. They're going to move off the same way they were before. When we talk about activation energy, we're talking about the kinetic energy of colliding molecules coming in, and that energy of the impact, if you will provide the energy necessary to stretch or bend or even break the bonds, or eventually break the bonds, maybe a better way to say that. The kinetic energy then is being converted into that chemical potential energy, which is stored in the bonds, which is causing them to stretch and get pulled farther apart. So that minimum energy required for a reaction to even be able to occur is what we refer to as the activation energy. So the bond has to be able to stretch a certain amount, or bend a certain amount, or have a certain amount of energy put into it to break it. And if you have less than that amount of energy, you will get no reaction from it. So that's what the activation energy is. It causes a higher energy state for your reactants, and we call that an activated complex or a transition state, and that will be temporary until it creates the final products. It is a very high energy state, and particles don't stay in it for very long before they will settle into a new state. So here's a sample of a potential energy diagram for a reaction. You've seen these before. On the left side you have the energy of the reactants, which is kind of at the bottom of the hill. And then as you work your way up the hill, that's basically where the activation energy is being added to your molecules. And in this case, it's causing the nitrogen and carbon triple bond to bend and get closer to the CH3 on the other side. So that is a higher energy state, because the most relaxed state is when they're 180 degrees apart. And then when you get to the top, you'll notice that that bond is pretty much broken, although there's an attraction going on there, which is holding it there. And that is a very, very high energy state. The electrons do not all want to be in that orientation. The particle is very unstable, and that's why you're at the top of the hill, and then all of a sudden all that energy drops off, and your carbon continues its rotation around to bond to the other carbon and make acetonitrile, which is a much more stable molecule than the molecule that this started with. And you notice that from where we started and where we ended, there's a delta E. That is the change in energy that we can measure, because when this reaction occurs, it will release that heat into the surroundings. And so if we have stuff in the surroundings to absorb that heat like water, then we can measure that change in energy. And so in this case, that delta E will be a certain value in kilojoules and will be released. So this will be an exothermic reaction because your products are lower than your reactants. So when we look at the Boltzmann distribution, you'll notice that we have two different situations here, one at a lower temperature and one at a higher temperature. So on the y-axis is your fraction of molecules containing that energy, and on the x-axis is the amount of energy that they contain. And so it's sort of like a bell curve, except there's no top to it, and you've seen this before in previous presentations, but you can see that there's a point where we drew that vertical line and we just said that that's the point needed for the reaction to occur, so that is our activation energy point. And you can see that at the lower temperature there are fewer molecules, there's a smaller area underneath the curve, demonstrating that there are fewer molecules that can actually have the activation energy necessary in order to react. And if you raise the temperature, you have a drastic increase in the number of molecules that will be able to react. And that's why small differences in temperature will have huge differences in your reaction rates, because you're adding so many more molecules now that have the possibility. The one example in the textbook showed a situation where you raised the temperature 10 degrees and your fraction of molecules able to react is going up by 3.6. So that is a very, very large increase for a very small increase in temperature. So temperature is a huge factor. Arrhenius did a lot of the initial studies with reaction rates, and he discovered that as the temperature increased, the rate of the reaction increased, but it was a non-linear fashion. And so eventually he came up with his equation, which is K equals A e to the minus EA over RT. And that explained this relationship that he discovered. K is the rate constant. The rate constant is experimentally determined, and it explains how quickly reactions will occur. Temperature is part of that constant, and there are other things that go into that as well. A is the collision factor, which is discussing the percentage of collisions that would possibly give you a reaction. It turns out that A is not changed very much by temperature and other factors, so it's fairly constant for each type of reaction you have. EA is the activation energy. R is the gas constant, which we use 8.314 joules per mole Kelvin. Joules is the same as kilopascals times liters, so it's the same as the gas constant if you were to have it in kilopascal liters. So it's 8.314 joules per mole Kelvin, so remember to use that on all problems and things that you do with rates. And T is whatever the current temperature is in Kelvin. If we linearize it, which those of you that came out of physics have done a lot of that, but if we linearize the equation so that the curve that his original equation gave us is now a straight line, we get this relationship where the natural log of the rate constant is equal to minus the activation energy over the gas constant. That's your slope. So that's how you can figure out your activation energy for a reaction, is when you graph the relationships here, you get that slope. And then your temperature is in the bottom, so your x value is actually 1 over the temperature plus, and then your y-intercept is the natural log of the collision factor. Okay, so we usually look at it in a different form where we look at the change in the natural log of K. So natural log of K2 minus K1 equals minus EA over R, and then it's 1 over T2 minus 1 over T1, and we just ignore the plus A part because you can read that right off of the graph. But you can see now that it's a straight line graph, it's going downward. So the slope of this is negative because as the temperature goes up, 1 over T gets smaller, but also as the temperature goes up, your rate constant will increase because you'll have a quicker rate. So that's why you have this negative slope. And that's why your activation energy is negative EA, because your activation energy is a positive value, but the slope is negative, so we put the negative sign in front of it to make the equation work. But the key here also is that as the activation energy goes up, it's going to cause the rate of the reaction to decrease. So when we want to calculate the rates, a car travels a certain distance with respect to time. So picture yourself in a car driving. If you graph that distance versus time for a car traveling at a constant speed, you will get a straight line. Your distance will keep going up. So if your car is traveling at 60 miles an hour, after 1 hour you'll have gone 60 miles. After 2 hours you've gone 120 miles. After 3 hours you've gone 180 miles. And it's going to be a perfectly straight line. The slope of that line is the velocity of the car, which we could also refer to as the rate that that car is traveling. So the rate of change of your distance versus the rate of change of time is your velocity. In chemistry, we don't have velocity, but we want to get the rate of the reaction, so we're going to do it by looking at the concentration of one of your solutions versus time to determine the rate. So in chemistry, we're going to look at the change in your concentration versus the change in time. For reactants, it's negative since the reactants are disappearing, which also means for your products it's going to be a positive value. And those are stoichiometrically related, and we'll see problems like that in class. When we take the rate of change in concentration over a long period of time, we can calculate the average rate. And that is good to know in some situations, but for the most part, the rate is not constant. Because as the reactants gets used up and the concentration of the reactants goes down, the number of collisions also decreases, and so therefore the number of effective collisions goes down and your rate begins to slow down. And if you want to go to the extreme, when you have almost no reactants left, they're rarely ever going to find each other, so at that point your reaction is almost stopped. So it has to decrease. So what we do then is we can calculate the instantaneous rate. In most reactions that we do in class, that instantaneous rate is right at the start. But if we did it for an extended period of time, we can calculate the instantaneous rate graphically, or we can use calculus to do it. So the reaction rate is always considered to be a positive value. And so we get something that looks like this if we're graphing the concentration of a reactant with respect to time, and you can see that it's not a constant value. So what we can do is we can keep taking our average rate and taking 2 points and moving them closer and closer and closer and closer together. And after a while, we'll get to where the 2 points are almost on top of each other. And that's basically when we get to a tangent line and can calculate the slope of the tangent line to figure out the rate. And this is what calculus does for you. And we're not going to do a whole lot of calculus in here. I'll show you how it works. But it's not important that you know calculus, but it is important that you understand that that rate is the slope of the line. And when it's curved, that slope can be determined by drawing tangent lines to your curve and finding the slope of that tangent line. So you can see here that the initial rate is significantly steeper than your rate at 600 seconds because your reaction is slowing down. So if the rate equals the change in concentration with respect to time for each substance, and again a negative is in front of it to make the rate positive even though your concentration of your reactant is going down, then we can write a rate law to demonstrate this for the overall reaction. And so what we would do is for a reaction that's n moles of substance A plus n moles of substance B equals your products, the rate would be equal to your rate constant times the concentration of A to the nth power times the concentration of B to the mth power. So K is the rate constant, which is where your temperature and everything shows up, so that changes with temperature and pressure and other things. N is the order of the reactant, and M is the order of reactant B. And when we talk about orders of reactions, we're talking about how much that substance affects the rate of the overall reaction. N and M must be determined experimentally. They're usually whole numbers, but they don't have to be. And if you add N and M together, you get the overall order of the reaction. What the order means is if a reactant is first order, then doubling the reactant's concentration will double the rate of the whole reaction. If it's second order, it means that doubling the rate of concentration of one of them leads to a fourfold increase in the rate. You can have a zero order reaction, which means that if you change the concentration of a reactant, it doesn't change the rate at all. And when you add up all the orders, it gives the overall reaction order, so you can figure out then if you doubled everything, what would that do to the rate. And we can determine K values and rate orders experimentally We will in some experiments. So when we come back to class, we will look at some examples of this. We will talk about the integrated rate laws, because I think that's a better conversation in class, and we'll talk a little bit more about catalysis.